Okay, sorry about that. And then our third type of steering, sweeping, or scanning, remember that those are all AKAs here. You should put them all down, is used with phasing. And if you're thinking like, well, is this the same phasing that we learned about before? Remember, it's also called automatic or electronic or phasing, time delays. Yes, it's the same one, but it is a little bit different. And so again, the same definition that it's the application of voltages to all elements with small time delays. And I referenced how small the time delays were before, and I was like, I think they're less than 1 microsecond, and there it is for confirmation. But there's a little difference in how time delays are used for scanning or sweeping or steering. Okay, so I'll go back to this one because I think that this one explains it the best. So here are the PZTs, the blue PZTs, and you can see that these electrical spikes here are going to reach the PZTs at various times, right? Like obviously because this one's the closest, the electrical spike to the PZT, it's going to get there the fastest, and because this one on the end is further away from the PZT, it's going to take the longest amount of time for it to travel down the wire and vibrate the PZT. When you look at the pattern of electrical spikes, it's in a sloped pattern, right? It's in a sloped pattern, not curved, in a sloped pattern. So what that does, look what it does, is it pushes the beam into a direction. So it scans, sweeps, or steers the beam. So ideally, we all of our patterns have to be curved, right? Remember, a small curve or like more curvature or less curvature will change the level of the focus and the level of the or the length of the near zone. But now we're learning like a different concept, right? So a curved pattern, so this is curved, will focus the beam, right? That's why it looks like it's coming to a focus right here. A sloped pattern, and this is sloped, will steer the beam. Steer, sweep, or scan. These are all AKAs, and that's why it looks like it's being pushed into a direction. So most of our transducers have some sort of pattern. So imagine if I take both of these, I take a sloped pattern plus a curved pattern, the end result will be something like this, where it's a little bit sloped and a little bit curved. And so then if you look at the result of the beam, not only is it focused, right? It's focused, but it's also steered in a specific direction. So now you guys kind of understand all three of them, right? So this first one is unfocused, right? Because there's no curvature to the electrical spikes. There's no slope to the electrical spikes. This second one has a sloped pattern, and therefore the beam is going to be scanned, swept, or steered. This third one, the voltages have a curved pattern, and therefore the beam is going to be focused. And then on this last one, on image 4, you have the combination of the sloped plus the curved, which results in this end result, and our beam is focused and steered in a specific direction. And so when you guys hear the word electronic automatic phasing, I want you guys to think of it as, you know, what does phasing do? Well, phasing can do two things. It can focus the beam, and it can scan, sweep, or steer the beam, which are all AKAs. And you know, remember how small the time delays are, less than 1 microsecond to accomplish that. So I think it's really helpful to draw pictures for these ones. And you know, you remember there's 3 types of focusing. What are the 3 types? There's 3 types of steering. What are the 3 types? And phasing is the same for both. So like, besides one being a slope pattern and a curve pattern, but phasing is a combination. So what I'm talking about is here are your 3 ways to steer the beam. And then earlier in a different lecture, I showed you guys this, which was our 3 ways of focusing the beam. And phasing is on both of those lists. Now, the next part that we're going to learn is we're going to learn about 6 different types of transducers. So I know you guys know a little bit about transducers. In chapter 1, he told us about a curvilinear, a linear, and a sector transducer. And so those were like really basic. It was really just knowing where the pulses start and how the pulses travel. Do the pulses originate at one starting point or at different starting points? Do the pulses travel in one direction or in different directions? Well, now you guys need to know about like 6 different transducers, and these are specific transducers. And these are, you're going to get tested on these. And for this part, the best way to do it is to memorize it, but it's a lot of memorization. So I'm warning you now. This is probably one of the hardest parts because it requires so much memorization. So this is transducer number 1. It's called the mechanical. So remember, I told you guys when we're talking about transducers, you remember mechanical motor. And if you do that, it will help you with the rest of it. It's also called a single element transducer. How many crystals? There's only 1 PZT inside of this transducer. The resulting image will be a fan or sector shape. So it'll be, you know, like something like this. How is the beam steered? Well, remember, I told you guys mechanical motor. So it's steered mechanically, which in other words means with a motor. And there's that picture at the top that I told you guys to draw. Beam focusing, it's fixed. So what does fixed mean? What kind of focusing is fixed for us? It's a curved lens or a curved PZT. And then what happens if the PZT breaks? Well, there's only one. So if the PZT breaks, you only have one of them in there. So that means the entire image is going to be lost, or your whole screen will turn black. And so this is our first transducer. And this is like the easiest one to remember. Some students are really creative and they like come up with like little pictures, like they'll draw the transducer, they'll draw the PZTs, they'll draw the image the way, you know, and then like they'll put an X through it to show you like that the, you know, if the PZT breaks, the whole image is going to be gone. And so you can get creative with it, but this is a lot of memorization. Transducer number 2 is a linear transducer. This one has 100 to 300 rectangular shaped PZTs. These PZTs are 1/2 to 1/4 wavelength in size. And so this is something you're just going to have to memorize again. The shape of the image is fan or sector, and this one often throws people off because the word linear is here. So this seems very odd. How is that done? You know, how is it a linear transducer? Well, it is linear because when you look at the transducer itself, it does have the flat surface. So it is linear, but when you look at the image, this is what the image looks like. So they kind of like don't match. And I think that a lot of people struggle with that. How's this beam steered? Electronic. Remember that this is called automatic electronic phasing or with time delays. How is it focused? In the same way, it is focused with electronic automatic phasing. And then also want to write down this is capable of multifocus, which we don't really know what is yet. We haven't really talked about multifocus, so we're gonna learn that later on. If there's a damaged PZT, the beam focusing and the steering becomes erratic. So it just means it just kind of gets crazy. I usually will draw something like this just to like represent crazy. And your picture just really won't make sense. And the footprint of the transducer is really small. It's less than 1 centimeter on each side. So this is a helpful thing to remember. Because it's so small, you're going to have pulses coming out in different directions. Remember, the transducer is small, so it doesn't really cover a whole lot of tissue. And this is where the beam steering electronic comes in, right? How are those pulses going out in different directions? Our next one is an annular phased array, and this one is very, very unique. Even if you look at the picture of the transducer itself, it kind of looks like a little rocket ship. It looks very different. So the common question on the SPI is about this one. This one has disc-like PZTs. So the PZTs actually look like this. They're like multiple rings that like are stacked and layered with like one common center. And so it says they are multiple ring-shaped elements with a common center. The resulting image is a fan or sector shape. The beam steering is mechanical. Remember, mechanical motor. So there's a small motor inside of the transducer. This is a really old transducer. I mean, look at it. Like, it looks old, right? It looks outdated. Any of those old transducers have motors inside of them. Beam focusing is done electronically. It's also capable of multifocus, which this is a really common SPI question. So they like to ask questions about the crystals and what's so special about this transducer, and it's capable of multifocus. If you have a damaged PZT, you're going to get a horizontal or like side-to-side band of dropout. And so this is what this represents. You're just going to get this black line across your screen horizontally. Clearly, this is really dramatic. I added this black line of dropout. It's never this big or this thick or this obvious, but I wanted to do this to help you guys remember. And then facts about this is that the inner sets of PZTs create a shallow focus. The outer crystals create a deeper focus. The location of the dropout from the damaged PZT depends on whether the damaged PZT is an inner crystal or an outer crystal. And then I created this image to kind of show you what that means. So this is like the inner PZT here, and this will affect the top of the screen. So if this inner green PZT is broken, the top of the screen will have the horizontal band of dropout. Also, if the PZT is not broken, remember I told you guys that this transducer is capable of multifocus. So this green PZT will be able to focus whatever's at the top of the screen. The purple, which is like in the middle, represents like the middle of the image. And then the blue on the outside, this is like the outer element or the outer PZT. If it is broken, you will see a horizontal line of dropout at the bottom of the screen. So I kind of color coded it. And so down here at the bottom, I just put that the inner elements are responsible for the superficial portion of the image, and the outer elements are responsible for the bottom portion of the image. And obviously you're going to have some in between, just like that purple area is in between. And so I want you guys to know that the location of the dropout from the damaged PZT depends on where the PZT that is damaged is inside of the transducer. Our next one is a linear sequential array. The linear sequential array has 120 to 250 rectangular PZTs. These are a little bit bigger. They're one wavelength wide, not like a half or a quarter. The shape of the image is rectangular, and the image is never wider than the transducer. So actually, if you were to measure from this part of the transducer to this part of the transducer, and then you measured from this part of the image to this part of the image, you would realize that they are actually the same, and they are about 10 centimeters. This is a pretty big transducer. Beam steering is done sequentially. So remember, small groups of crystals are fired simultaneously. The sound beams are parallel and going straight down into the body. And so remember, sequential means when you hear the word sequential, this is like the only time we're going to say it in physics. When you hear the word sequential, I want you guys to think about sequential, like, means small groups, and that'll kind of help you guys remember it. Like, it's small groups of PZTs that are fired off from one end of the transducer to the other in order. Remember, it's going to give us that really detailed image. The beam focusing, so earlier models, older models would have had a fixed focusing, so the curved lens or the PZT, and the modern models are using electronic focusing. If you have a damaged PZT, you're going to get a vertical line of dropout, so not a horizontal like the annular phased, but vertical. And then that picture in the top corner kind of shows you that vertical line of dropout. And then a fact about this is this transducer can also steer the beam electronically. So when we look at beam steering, it's done sequentially in small groups, right? I told you guys to remember small groups. Well, it can also be steered electronically, which you guys should know by now that electronic or automatic means time delay or phasing. And then in that case, if the steering is accomplished with using time delays, the resulting image would look like this. So it doesn't look like a square anymore, but now it looks like kind of like a shifted square, which is called a parallelogram. Transducer number 5 has 120 to 250 crystals, 1 wavelength wide. The image looks like a blunted sector shape. So the blunted sector shape, this is the one they're going to ask you about. The top looks like it's kind of like pushed in. That's what they mean by blunted. And beam steering is done sequentially. So again, small groups from one end of the transducer to the other in order. Beam focusing electronically. This one too, you're going to get a vertical dropout line when a PZT is broken, but there's so many PZTs, right? So it's not like you're going to lose the whole image. You're just going to get one line of dropout. And then a fun fact about this transducer is that it is also very large, 10 centimeters. So you're going to notice there's some similarities between transducer number 5 and transducer number 4. And then our last transducer is a vector or a virtual sector array. Sometimes it's just called virtual array. Just remember the V's, right? It could be called vector or virtual. This one has 120 to 250 rectangular shaped PZTs. The image is very unique. It's a trapezoid. So this is what it looks like. Flat top, and it kind of flares out at the bottom. So don't get your shapes confused, but so far we have like sector, blunted sector, trapezoid, parallelogram, and then beam steering and focusing are both accomplished electronically. So remember, with time delays, we don't really know what happens if the PZTs break, so that's not relevant, I guess. And then a fact about this transducer is that it's really, really small. So like I said, there's ways that you can study this. You can try to be creative, which is something I did when I was learning physics myself. I kind of created an image for each one. So, and my images were kind of crazy and like didn't always make sense to everybody else, but they made sense to me. So for example, what I mean by drawing an image, I would draw my transducer like this for transducer number 1, my mechanical. I would put that one PZT and I would remember that there's just like one PZT, and I would write like little notes. I would put my arrow, and that meant that steering is accomplished with a motor or like mechanically. And then my PZTs are going to come out like this. And this would help me to remember the image shape. So like the image shape would be fan or sector. And then if the fan, or if that one PZT was broken, my entire image was lost. So I would just put like a line through it like this. And then like, write down that like, if it was broken, my entire image was gone. And so on. And so I would create like little pictures like this, and I would write these on my whiteboard, and I would kind of like talk about it as I was drawing it out and kind of explain it to somebody else. And, I focused on, I'm going to spend, 30 minutes on one PZT, on one transducer. And then like, I'm going to spend the next 30 minutes with my second transducer, but I would like review the first and the second. And then I would spend like another 30 minutes with my third transducer, but then I would review my first, my second, and my third. And I kept doing this. Like I would dedicate 30 minutes to each transducer. So that means like I would draw my pictures and talk about it and use my whiteboard, and I would do it over and over and over for 30 minutes. And then I would review my 1, 2, and 3, just to make sure I never forgot my 1 and my 2, my first and my second transducer. And I would do this all the way up to 6. Some people create, so if you take crystals, image shape, beam steering, beam focusing, damaged PZT, and one more facts. So 1, 2, 3, 4, 5, 6. what you could do is you can create like a little chart where you can list like those things here. So like 1, 2, 3, 4, 5, 6, your transducers number right here, 1, 2, 3, 4, you have 6 transducers. And then a lot of students create charts with them. And so like, you just like fill in the chart, right? So like, for example, you know, like if this was like, what happens, you know, if this is like broken, I would write down like this one, like the entire image is lost. This one has like a vertical line of dropout. This one has a horizontal line of dropout. Like I would just like fill it in, and then students would start seeing patterns. They would start seeing like, oh, like this and this, you know, and this match. And then they would just remember how to fill in this chart. And you know, the more you do it, obviously the easier it becomes. So you can study that in 2 different ways, but you definitely should pick one way instead of like just saying them and like hoping that you remember these, because you probably won't. And when you guys get that white sheet of paper in front of you for the SPI, obviously they don't want you to brain dump, right? Like they don't want you to like dump all the things you have locked up in your brain on that white sheet of paper, but like who's going to stop you? Because it's not like you're cheating, it's inside your brain. So if you have it inside your brain, like it's not like you're looking at anything or cheating. And so a lot of my students, when they get to that SPI test, they'll brain dump, which means they'll just like write down that chart on that piece of paper. So when you finally reach those transducer questions on the SPI, you can just refer to the chart and, you know, like you'll answer those correctly. Okay, so multi-focus, we already know that like wherever the focus is on your image, that's going to be like the best part of your image, the most accurate. It has the highest amplitude, power, and intensity, because that's where the area of the beam is also at its smallest measurement, right? And so when area decreases, API increases, because those are indirectly related. So most newer machines have something called multi-focus, where it allows you to use more than one focus at a time. I want you guys to remember this, that one pulse can only have one focus. So what that means is whenever we draw a beam or a pulse, we've always drawn it like this, right? Like every single beam has only had one focus. It didn't matter if we like gave it a long near zone length or a short near zone length, it still always had one focus. Our beams, one single beam, one single ultrasound, it can't look like this. So like if you count this, like here's one focal zone, here's 2 focal zones, here's 3 focal zones. Like it cannot look like that. Our beams are always trumpet shaped. So one pulse can only have one focus. One pulse can only have one focus. Okay, you got to keep that locked into your memory. So how is multi-focus accomplished? How can it be that this image here was created out of 4 pulses when one pulse can only have one focus? So what had to happen here for this to happen? So I started off by telling you a sound beam only has one focus, right? That's what it is. And so like, for example, on these pictures, like this is not real, right? Like 4 is not a real sound wave. With a single focus, one pulse is emitted down each scan line. With multi-focus, more pulses are transmitted down each scan line. And so I'm going to draw this picture with you, and this will help put an understanding to like what multi-focus is. Okay, so go ahead and we're going to draw, oops. Okay, we're going to draw our, hold on. Okay, I'm going to do that again. Okay, so we're going to draw our transducer. So here's our transducer. And so what happens here, our pulses are coming out of the transducer. And let's say that our image, here's our image, has, I'm just going to do 3, has 3, and I'm going to color code them on purpose. Our image has 3 focuses, okay? So the first set of pulses comes out of the transducer, looks like this. Notice that there is a shallow focus on these, right? Because there's a shallow focus on your image, right? A second set of pulses comes out of your transducer and it goes down the exact same path, but it looks like this. So now the pulses look a little different. What's different about them is they have a deeper focus. So here's my green focus, my deeper focus, and that's because it's a deeper focus on the image as well. Then a third set of pulses comes out of the transducer at the exact same path, right? Exact same area. And these pulses have an even deeper focus. So here are my orange deeper focuses. And that's because there's like a deeper focus on my screen. So what ends up happening is one pulse can only have one scan line. But for multifocus to be accomplished, multiple pulses are sent out or transmitted down each scan line. Each scan line is like down each path, basically. So multiple pulses are sent down each path. Each focus has a different depth of, each pulse has a different depth of focus. So in other words, to understand how multi-focus is accomplished, okay, since one pulse can only have one focus, multiple pulses, each with a different focal depth, are transmitted down or like through each scan line. Or remember I told you guys scan line is like path, right? So this is how it's accomplished. So a common SPI question is they're going to ask you, if there are six, for example, if there are six focuses used on the image, does the pulse have six focus areas? No, a pulse can only have one focus. So how is it accomplished? Well, multiple pulses, each with a different depth of focus, are transmitted down each scan line. So that's what it's saying here. More pulses are transmitted down each scan line or path. So if we already know that the focus has like a really good effect on the image, it's going to improve detail, improve resolution. So multi-focus is a good thing. It has like a really positive effect on the image. However, it takes more time for the machine to do it. So it will degrade your frame rate, which is the rate at which frames are created, right? The rate at which images are created. If one image takes a long time to create, your overall frame rate, the rate at which images are created, is going to slow down. And then another way of saying that is temporal resolution. I know you guys don't know what temporal resolution is yet, but a lot of my students think of these as like they're always together. In fact, we say like frame rate, temp, res, frame rate, temp, res. We say that often together because they're always going to do the same thing. If frame rate increases, so does temporal resolution. If frame rate decreases, so does temporal resolution. It's like the little brother that gets dragged around to go everywhere where like the older brother goes, right? Like it's always like, take your little brother with you. And so it's kind of like that. They are directly related. They're always like doing the same thing. And so I know we don't know what temporal resolution is, but it obviously has to do with time because temporal means time. And so I want you guys to always think about like, remember how we talk about ultrasound, there's a good and a bad for almost everything. Well, the good is that multi-focus has such a positive effect on your image, but what's the downside or like the bad side of that, or the like pros and cons? The con is that it takes time. And so it takes a lot of time. So typically we don't scan with multi-focus mode. I normally tell you guys to scan with like one focus, or some machines are already programmed where like you have to use two. So like you can't go to a one, it's just with two. So you just use the smallest amount of focuses possible, which is usually like one or two. You never, if it gives you the option of scanning with like 7 focuses, you shouldn't do that. It's going to slow down your image and you'll notice it. Your image looks like it's lagging. It's like watching a video on YouTube when it's like constantly like buffering. Like it doesn't look like it's like a smooth video. You're like waiting for it to like catch up. And so that's what it looks like when you're scanning with more than one focuses. Not all the time, but a lot of times. All right. So in your book, you guys are going to go all the way to 58. And on 58, we are going to highlight what electronic focus is. And next to electronic focus, I want you guys to write down the word multi-focus because it means the same thing. And I want you guys to highlight, in addition to steering, phased or phasing can focus the beam as well. An increase in the curve delay pattern or greater time delays between elements moves the focus closer to the transducer, whereas a decrease or shorter delays in the curvature moves it deeper. So this is kind of what we talked about in that last lecture with focusing. Multiple foci or focuses can be used. One pulse can be focused at only one depth. And then this is a definition. Multifocus requires multiple pulses, each focused at a different depth. And that's the definition for multifocus. And then you can go back to your normal highlighter. Highlight echoes from the focal region of each pulse are displayed. And the rest of the image is discarded. So basically they're telling you what a multifocus image is. And they're just saying like, hey, the image is going to be really good because they're going to show you the echoes that are in the focal region, right? Like, and the rest of the image will like get kind of trashed. And so your image is really good. It's going to contain a bunch of really focused echoes. So he says the result of the image is a montage or like a group of focal regions from the different pulses, which will improve detail resolution. However, the use of multiple pulses per scan line takes more time, and the frame rate is reduced, which degrades temporal resolution. Thus, temporal resolution is the sacrifice or is sacrificed in this approach to improve detail. So that's like often how it is with ultrasound. If it has a really positive effect on your image, so for example, if I said to you, hey, like, I'm going to take this picture of you right now and you need to look amazing. Like you need to look the best you've ever looked. You're probably going to go shower. You're going to do your hair, right? Like you may or may not do your makeup. Like you're going to take time, right? So that you can look really amazing in this picture. Well, it's the same with ultrasound, right? Like anything really great on your image is going to take time. So therefore that's often the sacrifice with imaging. It's like, yeah, you can have that great image, you can have that high resolution, but the sacrifice is going to be time because it's going to take you longer to achieve that. On page 61, he's going to tell us about something called variable aperture. And I want you guys to write down next to it dynamic aperture. So let's break down the word variable. And I want you guys to do this with me because you'll see that this will really help you. Aperture. What does variable mean? To change, right? Or like changing. What does aperture mean? Element size. Okay, so like sit on that for a little bit. To change element size. Okay, I want you to think back in chapter 3. I have talked about aperture before, and I have talked to you guys about a small aperture and a large aperture. And those affected some part of your ultrasound beam. What do they affect? So like small aperture or changing it to a big aperture, right? To change the aperture. It was the near zone length, right? It was where the focus in the near zone length. So now I'm going to teach you guys about variable aperture. It's also called dynamic aperture, and the definition of this is having control over how many elements are used to transmit the pulse in order to control the focus in the near zone length. This is the point of it. If you're not talking about the focus in the near zone length when you're talking about variable aperture, then like there's no point to it. Variable aperture is changing the element size so that you can adjust where the focus and the near zone length is. Okay, so let me tell you guys, how many of you guys have been in the lab and you've taken a picture and your focus was up here, right? And then like 5 minutes later, you bring your focus down because you realize like, oh, I want it to be here, right? And then like 7 minutes later, you move your focus back up and you like put it right here. Like how are you able to just change the focus like that? How are you able to just adjust the focus? This is what variable aperture is telling us. So variable aperture has a picture in the book. It's on page 61, and it's those 3 red transducers, D, E, and F. And I really like those because I think that these are really helpful in explaining. So here you have the exact same transducer. In example C, all of the elements in the transducer are being used, right? So this is the same as having a large aperture, right? Because when the PZTs are together, we kind of think of them as like one big one. So it's a large aperture. What do large apertures do? They have a deep focus and a long near zone length. Okay. Now I'm using the same transducer, but only some of the PZTs are going to be used. The other ones that are white, they're kind of like blocked off. They're not being used. So I'm only using some of the PZTs inside of the transducer. This is the same as saying that there's a small aperture. Okay, small apertures will have a shallow focus and a short near zone length. So using the same transducer, whether you're using all of the PZTs or a few of the PZTs, will adjust number 1, the level of the focus, so where's the focus, and number 2, the length of the near zone. And so that's what variable aperture is. And so when our transducers are variable aperture, so whenever you're changing the focus around, I want you guys to think, oh, right now, when your focus is all the way at the bottom of the screen and you have that long near zone length, I want you to tell yourself, oh, I have variable aperture transducers. So right now I'm using all of my PZTs, which is the same as having a large aperture because my focus is at the bottom of the screen, which means I have like a long near zone length. When you move your focus up, well, it's not like you opened your transducer up and removed some of the PZTs, right? No, the PZTs are still there. You're just not using them. So it's kind of like they're being blocked out for a minute. Like they're there, they're just not given any electricity, which means like they're not ringing, they're not vibrating, they're not oscillating, they're not deforming, they're not sending out a pulse. And so I like this picture. This really like helps me understand. But also if you just like focus on the words, right? To change aperture and then dig down deep. The only time we talked about aperture was when we talked about the near zone length. So on page 61, I want you guys to highlight on the 4th line, not all elements of a phased array are used to generate all pulses. Smaller groups are used for shorter focal lengths, and larger groups are used for the foci of increasing depths. And the main idea is there, right? When we're talking about variable aperture, our focus and near zone length, you have to be able to know that that's why we're using them, to change the level of the focus and change the level of the near zone length. So in the future, when you guys are working, you might be the lead ultrasound tech, or you may own your own ultrasound facility. And people are going to come around, they're going to try to sell you different transducers and different machines. And so they're going to come around with a transducer and they're going to say like, hey, this transducer is variable aperture. or has variable aperture capabilities. And then you're going to be like, what? What's variable aperture? Well, that just means you can change the focus. You can change the near zone length, because some or all, of the PZTs are being used to generate each pulse. Okay, so he's pretty choppy in the topic that he's talked about today. At the end of chapter 3, I think it just gets like a little weird. Like ideas are starting to come together that like maybe necessarily aren't supposed to be. But here is an example of that. So on page 61, he talks about transducers. He says a single line of elements can focus and steer only in the scan plane. With at least 3 rows of elements, phasing can be applied to focus in the 3rd dimension. And then he says this dimension perpendicular to the scan plane is called slice thickness dimension or section thickness dimension. Next to that, I want you guys to write elevation or resolution. And then highlight, also called partial volume artifact. I want you guys to put a circle around that last part of the highlights where you guys highlighted this dimension perpendicular to the scan plane is called slice thickness dimension, section thickness, also called partial volume. I want you guys to circle that portion. You guys are not actually going to learn about that until page 68. So he basically put that in way too early. And then he jumped. So it's like he had like a moment where he said, so he started talking about transducers. And then he like started talking about elevation resolution for some reason. And then he went back to transducer. So it's really hard to like follow. The last paragraph highlight 2-dimensional arrays have the ability to steer and focus in 2 dimensions, which is called biplane imaging. So I'm going to separate it. If you guys have a Post-it, I would just write this on a Post-it and just like slap it right over that paragraph, because that paragraph is pretty bananas. So there's something called conventional arrays, and conventional arrays only have 1 row of PZTs inside of them. So those PZTs, when they're sent out into the body, they're focused and steered in only that 1 dimension. And so if you're like, I don't really understand, if you flip the page, go to page 62. So on page 62, image A shows you that. And I may or may not have referenced this to you guys before. So I know we can't see the PZTs inside of the transducer, but you can see how all the pulses that are coming out of the transducer, they're all next to each other. It's like one after another. They're all in one straight line. And so next to image A, I want you guys to write down that this is a conventional array. It has 1 row of elements. Focusing and steering is in 1 dimension only, and this actually creates 2D images. So like this will create 2-dimensional images. So like our normal black and white grayscale images. Okay. Image B, so right next to that, this is actually called a 2D array. And I want you guys to write down that this is called the 2D array. So it's not called a conventional, right? It's called the 2D array, and it has at least 3 rows of elements inside of them. Focus and steering is accomplished in biplane. So biplane means in 2 dimensions, which will create a 3D image. And this is a part that a lot of people get mixed up on. The transducer is called 2D, which means that it focuses and steers in 2 dimensions. Okay, like that's how you're going to keep it in your head. This transducer is called a 2D array. It focuses and steers the beams in 2 directions. That's why if you look at the picture, image B, you have pulses that are coming out vertically and horizontally. They're coming out in 2 different directions. Okay. How many rows of PZTs are inside of this transducer? At least 3 rows of PZTs, and the resulting image is a 3D image. So I think the fact that we say 2D and 3D in the same, talking about the same transducer is very confusing for people, and they get it mixed up. So again, if you think about it like that, it's called a 2D array because it focuses and steers beams in two directions. However, there's at least 3 rows of PZTs inside of them, and will eventually create a 3D image. And so this is, I have a hard time reading the text and like remembering it or making sense of it. But these two pictures, image A and image B, just like have really stuck into my mind. I spent a lot of time looking at those two pictures on page 62 and like talked about them and just like kind of studied the picture, like stared at them, and I like kind of picture the pulses coming out of the transducer, and I picture what I would see if I could look inside of the transducer. So I think like really vividly thinking about the pictures, like very creatively, has helped me like kind of memorize this, because I also want to call I want to call the transducer a 3-dimensional transducer because it creates 3-dimensional images, but it's a two-dimensional transducer that has 3 rows of PZT that focuses and steers in 2 dimensions, which creates a 3D image. So there's like a whole lot. But again, write these words next to the picture, and I have it like that in my book too, and that will help you kind of keep it straight when you're studying it. Okay, so now we're going to talk about something else that has nothing to do with anything we've learned so far. And we're going to talk about something called lobes. And so lobes are extra ultrasound beams, like little ultrasound beams that kind of go off in different directions away from the beam's main axis. Remember, the beam's main axis is like the beam itself, like the center of the beam. So these extra ultrasounds, books often refer to them as like squirts of ultrasound. They're just like these little random like squirts of ultrasound that are going off into some like random direction away from the beam's main axis. They're extra pulses, extra ultrasound, extra intensities. They're not as strong as the beam's main axis. But the thing about these, like, why does this happen? Well, we're going to talk about how we can get rid of it. But what's kind of crummy about this, and the reason we want to get rid of them, is if there's like something in the body here that's like a strong reflector, or the lobe comes in contact with it, like you got to think about it. You're angling your beam where you want to image. So on the image, you're wanting to see like what you're angling towards. You're not angling towards this like lump, let's say out here, right? But that lump will show up on the image because it got caught with a lobe. And so like the lobes themselves don't typically create any image, like anything to your image. They don't really affect your image typically, but every once in a while they do. So manufacturing companies, they want to get rid of this as being an option or like a possibility. So I'm going to talk to you guys about how they can actually get rid of them. So there's 2 types of lobes. There are side lobes and grating lobes. Side lobes are created when you're using a single element transducer, and it is sound energy that extends outside of the mains beam axis in the far zone. So this is what side lobes look like. So here you have your transducer, you have your single element transducer, and you have your pulse. Side lobes are in the far zone, so they come out like this, right? So those are the side lobes. And they're on the side of the far zone, on the side of the far zone. Grating lobes are a little bit different. So grating lobes happen from or occur from array transducer. So here's my array transducer with all of those PZTs, rectangular shape. And grating lobes, I think about them as like grating cheese. When you're grating cheese, it just kind of goes everywhere, right? So like grating lobes, they're kind of like all over the place like this. They're not just in the far zone. And these two are extra ultrasound energy that extends outside of the main beam. It can happen anywhere along the main beam, so not just in the far zone like the side lobes. So there are some differences, and you want to keep in mind that side lobes come from single element transducers and grating lobes come from array transducers. We don't really know how to get rid of side lobes. We don't know how to get rid of them because none of the books tell us this, and also we don't use single element transducers anymore, so maybe this is like why we don't talk about it, but we do use arrays. And because we use array transducers, we need to know how to get rid of grating lobes, and the two ways are with something called apodization and subdicing. So I'm going to talk to you guys about apodization and subdicing. Subdicing I'll talk about first because it's like super easy to understand subdicing. So subdicing is where one PZT is actually diced up, just like you would dice an onion or dice a tomato or whatever, diced up, subdicing into a bunch of smaller PZTs. So those small PZTs are put into the transducer, and that will get rid of grating lobes. That's like all we know about it. It's literally, look at the definition, to dissect the crystals into smaller pieces, right? Subdicing, dice them up. Apodization is a little bit different. Apodization is where outer elements are given a lower amplitude voltage than the inner elements. So here's a picture of grating lobes. You can see that they're kind of happening all over throughout the beam. This is a cool picture, but we're going to make it even cooler. We're going to make it make more sense. So here's our transducer. So go ahead and draw your transducer, and I'm going to give it some PZTs, and I'm going to give each one of my PZTs, and I know I'm like not matching them up nicely because I never do, but I'm going to give each one of my PZTs a wire. Remember, electricity has to travel down that wire to get to and vibrate and deform and oscillate the PZT. So what ends up happening with this is the outer elements are given a smaller amount of electricity than the inner elements. So I'm going to draw like a small drop of electricity on my outer ones like this. And as we go towards the center, that electricity gets bigger and bigger and bigger. With like the biggest electricity in the middle. And yours could be nicer than mine. But the outer elements are going to be giving a lesser amount or like lower amplitude of electricity. The center elements, right? The center element, that's a center. I know it looks like enter. Center elements are given the strongest or most amplitude of electricity. And so what this process where all of the PZTs, they're still all given electricity. So like that's not the main idea. And a lot of times when I ask students about apodization, they tell me like, oh, elements are given electricity using time delays. No, that's phasing. Yes, time delays are still being used here, but the whole purpose of apodization is to understand that there's like a different amount of electricity, like more in the center, less at the outside. So don't forget the purpose of apodization is not so like this picture here. This is why I don't like it. If you showed me this picture, I'd say like, oh, there's a curved pattern, so this beam is focused. Like, yes, right? That's true too. But like this part here, this doesn't show me different amplitudes. So like I always draw again, like my biggest electricity in the center, and then it's getting like smaller and smaller as we like get towards the edges. And that helped me to understand that, you know, there's more electricity given to the center PZTs than the outer. There is, so the advantage of apodization, obviously, the advantage is that it gets rid of grating lobes, right? Like that's why we're talking about it. But there's a couple cons or like disadvantages. Number one, it kind of broadens the beam a little bit more. So because it makes the beam a little bit wider than it originally was, the beam is getting wider, and that's going to degrade lateral resolution, which we don't know about our resolutions yet, but that's okay. Right now you just have to memorize that, and it will make more sense with the next lecture. And then it also decreases the sensitivity to the outer elements. So remember, those outer elements are not going to really acknowledge or use the weaker echoes because there's a decrease in the sensitivity to those. So I want you guys to kind of think of like apodization is a good thing because apodization gets rid of grading lows. That's why we're talking about it, right? However, with that reduction in grading lobes comes two disadvantages. One, the beam is going to get a little bit wider, which is going to decrease or degrade lateral resolution. And number two, those outer elements, those ones that are given the smallest amount of electricity, are also going to lose some of their sensitivity. So they're going to have a decrease in sensitivity. And we don't really know much about subdicing besides what it is. We don't know if there's disadvantages with it or not. All right, this lecture is not the toughest, but this is definitely a time where you should review everything so far in chapter 3. We should talk about what we know about the transducers. Number one, what's inside of the transducer? How does that work? How is frequency determined? How's frequency determined for a continuous wave transducer? How's frequency determined for a pulse wave transducer? You guys should be pausing and like answering me as I'm asking these questions as a review to yourself. You guys should be talking about, what's like the pros and cons to the damping or the backing layer. What's the purpose of the matching layer? What does, the case or the electrical shield, what do these things do? The wire and, the different components of the transducer. You should be talking about we talked about variable aperture today, like what is the purpose of that? What does it do? What is the purpose of gel? Why are we using gel? What's the pros and cons of multifocus? Also, how is multifocus accomplished? What are your 3 ways of focusing a beam? Remember, Bob, the guy who works at the manufacturing company, is going to do this. So he's going to determine one of the 3 ways to focus the beam, which ones are used for single elements, which ones are used for arrays, which ones are fixed, which ones are adjustable. What are your 3 ways of steering, sweeping, or scanning the beam? What are your 6 transducers? How are you going to memorize those transducers? Are you guys going to create charts? Are you going to create pictures? What's the difference between a conventional array and a 2D array? What else? And I guess this would be the last of it, the lobes. What's the difference in the similarities between side lobes, grading lobes? How do we get rid of grading lobes? Talking about each one of the options, which is apodization or subdicing. Remember, you got to talk about it, talk out loud, use your whiteboard. So this is a really good place to stop and review, because this next, like last half of the book, it's not really a half, it's like a few more pages. This really has it's like really on its own. So like you guys are going to get this all in the next lecture in one sitting, so you should be up to date before you join that lecture on everything you've learned so far. Go ahead and review, listen to this a couple times, change your notes if you miss anything. Each time you study a little bit differently. Don't get caught doing the same bad habit over and over and over. Keep it fresh, be consistent with your studying, but each time you study a little bit different. So you don't want to you want to consistently study, but you don't want to study the same information over and over and over consistently, right? Sometimes your notes, sometimes the book, sometimes your whiteboard, sometimes you're talking out loud. sometimes you're reading your lists, your flashcards, like your Quizlet, like you gotta do it all. Okay. Let me know if you guys have any questions. Go ahead and email me and we can find some time to discuss. And I hope you guys have a good rest of your day.